How can you use a PID control in order to control our robot? Let us consider a very simple system, but now it's not already 1D system, it's already a robot. It will be a planar robot that is able to move only in a plane, y-x plane. And we consider, let us start with the direct kinematics. Can you tell me the definition for direct kinematics?
It's the process of finding the position and orientation of the final vector or the final point of the robot by means of the general coordinates of the...
Sure. So we can do this exactly, and it will be the following. So we have two links. The first link can be described with θ1. The second link can be described by θ2. And in order to find x of this end effector, so it will be A, B, C, Cx will be AB times, what should I multiply? Cosine. Cosine θ1 plus BC cosine θ1 plus θ2. Do you agree? Sy will be AB times sinus θ1 plus BC sinus θ1 θ2. Do you agree? But still, it's very basic trigonometry, and since we use explicit representation, we can take a time derivative to compute velocity. For implicit representation, it's not the case. When we cover spatial kinematics, we cannot take just the time derivative of homogeneous transformation matrix to compute the velocities, but here we can. So this is the equation that I just wrote. We can assemble it in matrix form. We can take a time derivative to compute an motion of end effector, and it will be Jacobian times an angular velocity. Can you see it here? Raise a hand if you understood. So what didn't you understand? Let's start from here. Is it clear? Raise a hand if it's clear. Great. Time derivative. Cx. You need to take a time derivative. Will be AB times sinus. It will be with a minus. Okay, right? Sinus θ1 times theta times that. Do you agree? Then BC, actually minus here, minus sinus θ1 plus θ2 times θ1 with a dot, θ2 with a dot. Do you agree? Now, instead of this, we can write minus BC sinus θ1 plus θ2 times θ1 plus, actually minus BC sinus Phi1 plus T2 times θ.2. Do you agree? Okay. So here you can see we have θ.1 here, θ.1 here, and θ.2 here. We can write the following: AB times sinus Phi1 minus BC sinus T1 plus T2, and all of this has to be multiplied with the theta dot. Okay, so we can actually make a matrix. It's like, if you do remember, AB times CD will be, what it will be? AC plus BD. Okay? It's called linear combination. So it will be like A, like B, it will be minus BC sinus theta 1 plus theta 2, multiplied with the Q dot 1. Okay, do you follow now? So if I'll write the same for the CY, I have the second line here, and this matrix that describes geometry is called Jacobian. And this is the vector of angular velocity. And Jacobian maps velocity of end effector with angular velocity of joints. Okay. And actually, we can do the same for all points. For example, in order to compute potential energy, we need the distance for the center of mass, right? So in order to find position of this point, center of mass of second body and for the first body, we need to do the following, but to take just y component. Y component will be the h, the height. Potential energy, it is mjh, so this will be the h. Okay? Now, is it clear? Raise a hand. Great. Okay, so it was the direct task. What is the inverse? Yeah, inverse is to find theta 1 and theta 2 if you know position of end effector. For example, it can be the trajectory that you want to follow. So you have a trajectory for a welding, for example, and you want to follow it. So you already know what it should be, and you want to compute theta 1 and theta 2. So right here, we can do the following. So let's assume that this is our system. And you know the trajectory. Let us call P will be the trajectory that consists of x and y. Right? It means that you can compute AC. AC, the magnitude of AC will be x in power 2 plus y in power 2, right? Now we can think about ABC, this triangle. And you can remember the cosine's law. Let us suppose that this angle is beta. We can write the following. AC in power 2 equal to AB plus BC minus 2AB BC times cosinus of beta. Do you agree? From here we can say that cosinus beta equal to AC minus AB in power 2 minus BC in power 2. No. It will be opposite. AB plus BC minus AC divided by 2AB times BC. Do you agree? Great. And B will be nothing else as arc cosinus of this guy, like this. AC we know, we have the trajectory, right? BC and AB just constants. It's the length of our links, so we can compute it. All right. We can do the following for this angle, and it will be alpha. So you do understand that you can do the same, and you will left with this. All right. So since right here is pi, this is theta 2. Theta 2 will be pi minus beta. Okay? This is theta 1, and this is called gamma. Gamma can be computed as a tan of x do you have it here? It's like it's arctangents of this angle. An angle can be computed from the understanding of y and x, so like this. Do you agree? So tangents will be y divided by x, if I'm not mistaken. And theta 1 will be gamma minus alpha. Okay? And this is how can you solve inverse kinematics for very basic case of planar robot. For a spatial one, it will be more complex, but now we need to understand the ideas. Okay? So if you have a trajectory, the desired trajectory, you can compute the desired angles, right? So if we go back right here, you know the desired angles. You can measure the actual using position encoders or other kinds of sensors that measure position, and you can compute the error. And then you can use this equation to compute how much torque you need to apply in order to move along this trajectory. Let's have a demo. And by the way, you always have left and right solution when we talk about inverse. It could be, it's like you can go to this position like this or like this. And here you can see equation for the right and left solutions. Okay, now let us have a demo. By the way, it will be your second practice task. So here, what can you see? It's another live script, and right here you can see parameters of a robot. The length of first link, the length of second link, dimensions, mass, and coefficients for the controller. P, Kp, Ki, and Kd. Then you have a trajectory, and let us just run it. And you will see how robot is able to move. Okay, so here you can see how robot is capable of moving. You can see that it follows a circle. So regarding the simulation model, I need to explain you what it is, I guess. But let's skip it for the second part of the lecture. Right here, what can you see? You can see a joint, and as the input we send torque, and right here in the converter you can see that units exactly Newton per meters. It is really torque. So here you can see a PID. In the PID you need to put a proportional, integral and derivative component, and as an input to the PID we send the error, and the error is nothing else as the difference between desired angle or desired position and actual. Right here we have a sensor position that measures radians. So here you can see Newton's radians, and right here is nothing else as just function that computes something that we just write here. So you can see here, for example, tan y and x. Yeah, I was correct. And all these components. So just a function that computes those terms. Saturation, yeah, there is saturation, and we can just unlimit. Let's play a game here. Without saturation, let us take a look. Saturation, it is just limits to the output torques. Let us apply. It still can move, but you see how fast it goes from initial position to the trajectory. Now let us take a look at the plots. So here, what can you see? You can see a desired trajectory in red. So, can you see it? Let me fix it a little bit. And now it's a little bit better. Or, let me increase it. Yeah. So now you can see a desired trajectory, and you can see also an actual trajectory. A question for you: why do you think our actual trajectory looks like non-smooth trajectory? Is it really it went to this trajectory?
Hello, sorry for being
okay. Sure. If we increase discretization, it will be smooth, but the simulation will be slower. Yeah. Okay. Another case here. Those are the desired and actual trajectories, I mean angular positions. And you can see that for the second link, it's pretty much coincide. But for the first one, it is not. And the reason is not optimal coefficients. We need just to tune it. It's another story how to do this, but still we can do this. All right. And right here we can see the response transition. Yeah. You can see how fast it is because of the coefficients. If we use not so great coefficients, the transition will be not so fast. But since we use very huge coefficients, it fast. But also, if we take a look at the torques, by the way, it's Newton per meters. Yeah, there is no such a driver that can produce such amount of torques. It just do whatever we ask them to do. I mean, the initial position was like this, and the trajectory right here. And the robot with a certain amount of gravity went here less than, and it took less than 0.2 seconds. So it needs a lot of energy to go there, and it's pretty unrealistic. This is why I used saturation. By the way, speaking of contact, what do you think will happen if we're going to use PID control without saturation to interact with the environment? By the way, according to our rule, we can use position control only and only if the robot is isolated. Do you remember this? But why is that? Let us suppose that we use PID control to follow position control, to implement position control, and your robot interacting with the environment, and we use this kind of contact modeling. What will happen?
What's the desired motion?
Any trajectory. Let's assume that we do some kind of motion, and suddenly we put an obstacle. What will happen?
It will constantly generate forces because the error will be constant, but he doesn't understand that there's an obstacle, the controller.
Yes.
Will generate
He will try to do the task to decrease the error, but since there is an obstacle, he will try to increase torque. It means that it will apply so much force, so eventually it will just go inside. So and the force will be rising until it become greater than this force. And after that, our robot will just go through the object. This is actually, it's not a very good idea to use PID control, because in real life it will be the same. It's like your robot will try to damage an obstacle, maybe a human. So it will be just dangerous for environment, for a human, for the robot.
But I think the most dangerous part of the controller will be the KI, because when the error is constant.
It's like if we use the constant coefficients, we choose the coefficients such as we follow the trajectory precisely, but if we interact with the world with the same coefficients, it will produce just a lot of torque if it hits an obstacle. Okay, so now let us try to add saturation. Apply. Saturation, apply. And let's take a look at the plots once again. So now you can see that the torques were saturated. We can make it even smaller. And actually, it's the reason why the settling time now is greater. Before that, it was 0.2, and now it's more than 8 seconds. Still, I suppose that if we tune another kind of coefficients, and if our initial position will be closer to the desired trajectory, the settling time will be smaller. Okay. Is it clear, the concept? Okay. We have a break in 3 minutes, right? Right? Okay. So after the break, we will speak about model-based control. It's like right here, we didn't have any model of our robot. I mean, what is a model? We grounded that when we talk about model, we mean the equation of motion. So it's equation of dynamics. And right here, right now, for PID control, we didn't use any equation of motion, right? It's still possible, but if you'll change, for example, a mass, a length of a link, coefficients must be different, right? Because those coefficients only for this system. But for example, your robot takes an object, the mass of the system is different, and it will not be follow the trajectory. What can you do to make your controller better is to consider model base. We can derive an equation of motion, and in this case, if your mass, link mass will be changed, for example, in this case, you do not need to tune your coefficients of controller, you just need to tune your model, and that's it. It will be just more convenient. So we will try to do this, and we will how can you implement it. So this will be the topic for the next lesson. Also, we'll cover the other kind of control, force control and impedance control. Also, I'll show you an example. And also, we'll have a quiz. And then I hope that we will cover the material for the fourth lesson, lecture. Okay, so that's it for now. Now we have a break for 10 minutes? 20 minutes, all right, 20 minutes break.